We're going to keep talking about recovery. So remember last time we introduced the goal of recovery, which is to ensure that any committed transactions at the time the the database system crashed are in fact reflected in the state of the database after recovery, and that any transactions that had not committed, their effects are removed from the state of the database after recovery completes. And we introduced this notion of write-ahead logging. As a mechanism for enforcing recoverability. So what write-ahead logging does, if you remember, is that, well, basically you log the operations that you're going to do into the log before you actually do them. So that's the write-ahead part. And you further have to ensure that whatever the log, which is going to be stored on the disk along with the data itself, you have to ensure that the log records get written to disk before the modifications to the database itself do. Right? And the advantage of doing this is that now you can consult the log to figure out which things actually were applied into the state of the database and which ones weren't, and you can undo and redo things appropriately. Okay, so we have to undo operations from uncommitted transactions. And we have to redo operations from committed transactions that hadn't made it to disk yet. Okay. And we talked a little bit about how logging actually is going to work. So the undo, we have to do sort of two passes over this log, a pass from the sort of beginning of the log to from the earliest point in the log to the end of the log in order to reapply, do this redo pass, and then a pass from the end of the log backwards to remove the elements of transactions that had yet to, that have to be undone. Okay? So this is kind of the basic plan. We employ write-ahead logging. We use undo and redo to sort of reapply or remove operations from the database system. That's how we can ensure recoverability and this durability property that we want. So the goal for today is to talk about this specific system called Aries, which is the reading that I assigned for these two lectures. And Aries is it's considered the gold standard of logging protocols. It deals with a lot of kind of subtle and complex issues. Okay, so some of the things that Aries can deal with, or is able to deal with. So first of all, it's able to deal with both of these situations, undo and redo. So efficient support for both undo and redo. Okay, so that's sort of the starting point. But especially when they say efficient, they especially mean at runtime. So low runtime overhead, meaning one sort of critical concern is that they want is lightweight checkpoints. So we'll talk about checkpoints in a minute. But in effect, a checkpoint is going to be a point where the system is it's the sort of place the recovery is going to be able to begin from. And so if you think about how you implement checkpoints, like you want to have checkpoint as the sort of a place where you know all the dirty data maybe is flushed to disk, right? And so that's a point where you can, where you don't have, or you can sort of start recovery from. So the simplest way to write a checkpoint would be to stop running transactions for a while, and then take all the transactions, let all the transactions in the system commit, and then force all the dirty pages to disk. Right? And if you got the system to that state where there were no running transactions and all the dirty pages were on disk, you would know that you could restart recovery from that point in time, right? And the system would be, you wouldn't have to keep any log before that. The problem with this checkpointing mechanism is it's very heavyweight. You have to stop running transactions in the system for a while, right? So what Aries develops is a checkpoint mechanism that doesn't require you to stop running transactions in order to implement recoverability. So support for complex operations, e.g. Index updates. So things that simultaneously modify the heap file and index. And we'll talk about why these kinds of compound operations make recovery complicated. Escrow operations. So this turns out to complicate the system quite a bit. Escrow is this idea that, escrow is what people mean in database systems when they say escrow operations is essentially logical operations that increment or decrement counts. So for example, if you're maintaining an airline reservation system, you might use these so-called escrow operations to make a reservation or cancel a reservation. And the kind of cool thing about escrow is if you think about having a bunch of concurrent people who are, say, purchasing airline tickets, you can allow concurrent reservations to happen, like people to concurrently purchase airline tickets, which are rights maybe to the same row in the database table, which is the number of free reservations. You can allow those operations to happen concurrently as long as you guarantee that you don't go below 0 tickets. Right? So if I have 200 seats on an airline, as long as I don't have more than 200 outstanding transactions, purchase ticket transactions, I can allow those things to run concurrently because the operations themselves only decrement or increment the total number of free seats available. And so those increment and decrement operations can kind of be interleaved in any arbitrary order, and you'll still get the exact outcome. So there's this sort of extra special category of updates that involve increments and decrements called escrow operations that they wanted to support explicitly, and this is going to complicate the recovery procedure. And then the last one that we'll talk about a little bit is crashes during recovery. So what if the system is partway through recovering and then crashes? Okay, and these are all things, with the possible exception of escrow operations, these are all things that you're going to want in any database system, really. And so these are the kind of things that we'll talk about how they provide. Hopefully I can avoid slipping on this puddle here and breaking my neck. Okay, all right, so let's talk about how it works. So at a high level, it works sort of like we talked about last time. It uses undo and redo in order to reapply operations. It specifically prescribes, however, how undo and redo should work and the order in which they should be run. And it adds an extra phase. Okay, so it starts with what they call an analysis phase. Really what analysis is about is trying to figure out what needs to be done. During recovery. So it's sort of analysis is a pass through the log to analyze a forward pass through the log, that is from the start of the log or an earlier part of the log to the end in order to figure out what sort of work we're going to need to do during recovery. It's probably possible to design a system that combines analysis and redo together if you think about it, but they explicitly state it as a separate pass through the log. Okay, then they do what's called redo, and in redo, they call this, as I mentioned last time, repeating history. Okay, so this is a pass from the tail of the log forward, from the start of the log forward, and what they do in the redo pass is something that's a little bit unusual. They actually reapply all of the operations that appear in the log, whether they belong to committed or uncommitted transactions. Okay, so even if they know that a transaction is eventually going to abort, they still reapply its operations at redo time. Okay. They further prescribe that these. Remember, we talked about last time that log records can be physical versus logical. They further prescribe that redo logging should be physical logging. Okay? We'll talk about why in just a second. And for undo, they undo the losers. And they prescribe that you have to do logical undo. So logical logging. Okay? So these records have both redo and undo information in them. And so let's, so they do this, and they have this kind of funny prescription. They have physical logging, physical redo, and logical undo. So they call this physiological logging, which is a stupid pun. Okay, but what they mean is physical redo and logical undo. Can anybody, this is a little bit hard to understand why, but can anybody, why do you think we need to do, I maintain that it's a requirement that we do physical redo logging and logical undo logging. Anybody see why that might be the case? Yeah?
There are linking components to a single update, like updating on the indexes, updating the file. I think having just a logical thing there complicates the redo procedure.
Okay, good. Good. So for redo, we have to do physical redo for basically the reason it was stated, which is that these operations are not a modification just to a single page in the database, right? These operations that we're doing, because of these complex operations that involve, for example, like a log record, like an insertion of a log record into, an insertion of a record into a B tree, which may cause multiple pages in the B tree to change, as well as the underlying heap file, right? It's possible that if we're in the middle of applying an operation like that to the database system, why we just decided to do that. If we're in the middle of applying an operation like that to the database system, we might crash. So suppose we get halfway through. We insert a record into the B tree, but we don't update the underlying heap file. Okay? If we've done logical logging, if our logical log record simply said insert the value A into database table T, right? Then the problem we would have is that we wouldn't know how far we got through during doing that insert operation. So we have to actually record the, in the log record, the physical state of all the objects that we're about to update, so that we can make sure that they have the right physical image on disk after we do recovery, right? So we need to make sure that the actual B tree is consistent with the actual heap file after we do this redo pass. If we just wrote the fact that we're supposed to insert a log record into the B tree, we would have a very hard time. We'd have to do something very complicated in order to scan through the B tree and scan through the heap file in order to ensure that it's consistent with this operation at recovery time. Yep?
Why can't you just have a logical log for every single change that you make to the B tree?
Well, because those things, so you might be able to do that at some very low level, right? Like you might be able to have multiple logical log records and then group them together somehow and say that these logical log records are actually a part of this single larger update. I still think it's going to be hard because there are going to be these, like, you really have to ensure, if you're going to do that your logical log records are written in a way that the operations that are being recorded are truly atomic as far as the database system. So you need to guarantee that the system can't crash sort of like halfway through applying any one of those logical operations. And it's pretty hard to do that because, like, as a programmer, do you have a very good model in your head of whether a single disk write is truly atomic or not, or what number of bytes you can actually write to a disk block and have it be atomic, right? So it's much, much better to have an actual a physical record of the bytes that you're about to write, as opposed to the fact that you're about to make some transformation to a record without understanding the exact physical nature of that transformation, if that kind of makes sense.
Does idempotency have anything to do with it? Because I feel like if it's physical, then you can just apply it without really thinking about it. Where logical, you might have to check if it's already there or not, and then apply it or not. Because if you don't want to increment something twice if you only went through it once or something like that.
Yes, I mean, so that's another concern, right? We need to be really careful about these. And actually, I think that these escrow operations are going to sort of further complicate things. They're going to actually have to be a little bit careful at redo time that they don't redo stuff for because of these escrow operations. But yes, I mean, idempotency is a part of this, and this is really going to come up with the issue of why we have to do logical undo. Okay, so let's talk about logical undo. You guys cool with why we have to do physical undo at some level? Okay, so now logical undo I think really is sort of what was suggested. So the challenge with logical undo is, now imagine I'm redoing, think about my log. So suppose I have some transaction like transaction 1, okay, which does, so this is my log, transaction 1, suppose it does an insert of some value A, and then transaction 2 comes along and does an insert of some value b, maybe into some heap file or something, right? And now suppose transaction 2 commits. And the system at this point crashes, okay? So now we have to undo transaction 1, right? But we don't have to undo transaction 2. So if transaction 1 is not going to see the state of the database system at the time that transaction 1 wrote this log record is different than the state of the database system at the time that transaction 1 is undoing this log record. Okay, so that means, for example, the B tree, right, might have a completely different set of pages in it, right? The structure of a B tree might be completely different at the time that T1 is undoing this insert than it was at the time that it was sort of writing this log record. So if we wrote a physical undo record here, then the problem is that that physical undo record might reference a physical state of the pages on disk that is different than the physical state of the pages at the time the undo is being applied. Right, because in particular, at the time that we're undoing this transaction T1, this transaction T2 has come in and modified the state of the database in some way. So we better sort of have a logical record of the fact that we need to undo something. Okay? Now we don't have to worry about this issue where the database system might be in this partially completed state at the time we're doing undo, because as we did when we were doing redo, because during the redo pass, we guaranteed that we replay everything that was in the log. So after we do the redo pass, the database is completely consistent with the logical operations that we have run up to the point that the system crashed. Okay? But we do have to do this logical undo because we can't be guaranteed of the exact state of the physical pages on disk at the time that we apply. Does that kind of make sense? Okay. And notice that we're not worried about the, that we don't have this issue when we're doing redo of the physical pages, somehow having a different structure than we did at the time we wrote the pages out, because we're sort of redoing from the very beginning of the log forward, and we're replaying everything. And so we can, and because we're going to have this specific set of rules that tells us whether a physical operation has already been reflected in the disk or not. We'll see that when we're talking about how redo works. So redo will only reapply changes in exactly the order in which they were originally made, so we don't have to worry about this kind of issue we have with logical undo, or undo in general. Okay, so let's talk in a little bit more detail about what Aries actually maintains as it runs. Okay, so Aries maintains, for every log record that Aries writes, the log records contain some information in them. So it's similar to the information we described last time, but let's just kind of reiterate. I want to make a couple of definitions really explicit. So it keeps what's called a log sequence number in every log record. Okay, so this is a log record. And every log record has a log sequence number. This is just a monotonically increasing number that gets incremented by 1 for every log record that gets written. It also has a transaction identifier. So this is the ID of the transaction that's running. It has a little bit of other state, but the main other state that it has is this undo image. Okay, so this is the logical information it needs to do undo, and this redo image. Okay, and this is the information it needs to do redo, the physical information it needs to redo. And so as we said, this is logical, and this is physical. Okay, now for disk pages, by disk pages I mean disk heap file pages, not just heap, sorry, any disk page, like an index page or a heap page or whatever. It stores the page information, and on the page, so it stores whatever data is on the page, but on every page, it requires you keep what's called a page LSN, okay? Which is the log record that last updated this page before this page was flushed. Okay, so we keep this little bit of metadata. It just says, the last log record that has been, whose effects have been reflected into this page is the page LSN. So that allows us, when we're applying log records, to check and explicitly see whether a given log record has been applied to a page or not. All right. Okay, so now we understand. So these are the basic things that we write in log records. We understand a little bit about the philosophy. Now let's understand what we actually do during logging. So we're going to break this down into kind of three components. Three stages. So the first stage is well, let's call it two stages. There's kind of the normal operation, so as we're running without crashing, and then what happens during recovery itself. So let's start by talking about normal operation. So during normal operation, we have to maintain some data structures that are going to make recovery more efficient. And we also are going to periodically do things like write these checkpoint records that are going to allow us to sort of truncate the log and reduce the amount of work we have to do during recovery. Okay, so so there's two data structures that we maintain. The first one is the transaction table. Okay, what the transaction table does is it's a table of transaction ID and what we're going to call the last LSN. Okay, so this might be transaction ID 1's last LSN was 13, for example. Okay, so this last LSN for a given transaction ID is the most recent log record. That transaction ID wrote. Okay? So this transaction table is it's all the outstanding transactions. So when a transaction commits, we can remove it from the transaction table. And whenever a transaction writes a log record, we just update this last LSN field for that transaction. Okay? And then the other data structure we're going to keep is what's called the dirty page table. Okay, so the dirty page table, it's just the page, it's just the buffer cache in the system. So it's just a list of all the dirty pages in the system. But for every dirty page in the system, we're going to maintain what's called a recovery LSN, which is the log sequence number of the first transaction log record that dirtied the page. Okay, so this is dirty pages plus what's called the rec LSN or recovery LSN, which is the first log record to dirty each page. Dirty each page. Okay, so this last LSN is the last log record that a transaction wrote. The dirty page table is the first operation that dirtied the page since that page was last flushed to disk. Okay, so this is the buffer cache, so we will eventually, sometimes we'll write pages back to disk, and when we write a page back to disk, and remove that entry from this dirty page table. Does that make sense? Just think of the page as just like the buffer pool that you built in Simple DB. Any questions about these? Okay, so this is like, you can see that like we already have a lot of little moving pieces here, and there's still a little bit more to do. The protocol it's kind of complicated and fiddly and nitpicky. We're going to go through a really detailed example of how it works. Hopefully, it won't be too painful. Okay, so in addition to maintaining these two data structures, we get to do two things during runtime besides the usual processing of transactions. We can flush pages asynchronously. Okay, and what I mean by flush pages asynchronously is that the system is sort of free as a background operation to write pages back to disk whenever they want, whenever it wants. And the only thing it has to do when it flushes pages is update this dirty page table. So when I do flush a page, I go remove the entry from the dirty page table, but I don't write a log record. And I don't have to stop doing anything. I can just write a page back if I want to. Okay? And that's kind of nice. Even the buffer pool can just put its pages back to disk as it chooses to, if it wants to, or the database system may have some process that's periodically running to just write dirty data back to disk to make sure this dirty stuff is back on disk. Okay? And they can also take a checkpoint. And what all a checkpoint consists of in Aries is that you have to write out the transaction table and the dirty page table. So you don't have to do anything to running transactions. Running transactions are not affected. You just take a snapshot as of the transaction table and the dirty page table and write them to disk. Okay, and we'll see how we can use these checkpoints to determine where we can truncate the log in just a minute. Okay, so the kind of process is we're just going to chug along. We're going to do operations. We're going to write log records to disk, and then we're going to end up with some, and then we'll use these data structures that we've been keeping track of in order to implement the recovery process. So we're going to go through, basically what I'm going to do is just walk you through an example of how this works. So I'll write our example up here, and I'll actually hand out a piece of paper with it on it as well, and it's in the slides if you guys want to follow along, but I'll put the slides up here. So the example is going to consist of just 3 transactions writing 13 log records. Okay, I won't write all the log records out right now. We'll do that on the slide in a minute. But let's just write down the 3 transactions up here, sort of as a reminder. Okay, so here's transaction 1. Okay. So transaction 1, it's going to do a write to some object A, and then a write to some object B. Okay. Then at this point, the system is going to take a checkpoint. So I'll write CP here for checkpoint. And then transaction 3 at this point is going to start. Okay. And then the system is going to, transaction 1 is going to write some operation, some value C. Okay? And then at this point, the system is going to flush records A, B, and C. Remember, we don't write a log record for this, but we're going to record this flush operation for our sort of, to illustrate how recovery works. Okay? And then at this point, transaction B is going to start shorter here. Okay, at this point, transaction TID2 is going to start. So we've got TID3. Okay, so TID2 starts. TID2 is going to write some value D. Okay, and then at this point, transaction 1 is going to commit. I'm going to make transaction 1 a little bit shorter, so I have room. Transaction 1 is going to commit. Transaction 3 is going to write this value B, which is okay because transaction 1 is now committed. Transaction 2 is going to write some value A. Okay, and then transaction 2 is going to commit, and then transaction 3 is going to write some value E, and then the system is going to crash at this point. Okay, so at the end of this, transaction ID 1 and transaction ID 2 will have committed, transaction ID 3 crashed, and we're going to have a big log. Okay, so I'm going to, why don't we take a little break? I'm going to hand out 2 pieces of paper. Just so you need to take 2 different distinct pieces of paper. Unfortunately, they got copied onto, instead of front to back, onto 2 separate pieces of paper. So you should have 1 piece of paper that has this log structure on it, and then 1 that has the data structures that we're going to maintain as we go. So I'll pass these around, and then you guys can go ahead and take a break. So we'll come back at 3:10 on that clock up there. Just pass those. We'll take 2 pieces. that? Yeah, I did put it on there, sorry. I give you 3, and I just messed up. We'll figure it out. Everybody needs one. Yeah, everything's on. So these examples are in the slide deck that's posted online. These are just slides kind of copied out of the slide deck that's online, basically. So we're going to walk through the slide deck now, but the slide deck has some animations on it. And I think it's useful to have this in front of you as reference, basically. Did you figure out your problem? Did you reply to her problem? It's like it's really easy to have your
So I just want to ask about so let's say you insert some people and then actually inserts way.
Yeah.
And then you crash.
Yeah.
What do you redo? You just insert that tuple again. Then you
We're going to talk about this.
we redo everything.
So, well, we won't actually end up redoing. So repeating history, the only thing that what repeating history means is that the relevant point is that we're replaying, we're going to ensure that even transactions that will eventually undo, their results will be guaranteed to be applied. So that's what we mean by repeating history. You'll see during the redo phase, we're actually going to check to make sure that we don't repeatedly apply some operation that's already been done. Okay? We're going to figure out how we do it.
I still understand. I understand what you're saying. Like something's happening.
Yeah.
That makes sense. But why can't you have a check? And you know at the point that you autological operation.
Because you still are at this point. Okay, so you're right. Like at some conceptually, if you want to think of a checkpoint as a physical log, the exact status as of some point in time. If you're willing to write the exact state of the checkpoint, and I think what you said before, write the exact state out and then apply it. Right, so that's what they want to avoid ever having to continue to write completely flush all the pages in the database. Exactly. Because that would take a long time to install it.
Because this checkpoint's all shallow.
And it's also because they, like that would work and in fact some of these main memory systems actually work this way, where what they do is they basically write out all the pages in memory, and then in recovery, what they do is they load those pages into memory and they apply them. But in a big database, these pages you can't get the whole database into memory, and so you're going to have this the pages are going to reflect this kind of I just think it's pretty hard to figure out how you really would ensure that because you're flushing these pages back to this, like in a main memory system, you're not going to be really flushing partially written pages back into the database file generally. But you're going to be flushing these pages back. So I guess you can always go back to the checkpoint and sort of restart replaying transactions from that point. And that would work. Right. I think the key thing is that we don't want to have to write them in one big sequential blob, right? And I think there are clever ways. People have worked out clever ways to write complete checkpoints in the database actually asynchronously as well. And you might be able to make this work out. I wouldn't view what we're talking about as the only way to possibly implement a system like this, but it's one that has been repeatedly reapplied and it works, and so that's this isn't like some deep, I'm not trying to propose some deep theorem about what is correct or what the only way to implement it. Yeah. Okay, does that kind of make sense? Okay. Okay, all right, good. All right, let's go and get started. Okay, so we're gonna starting from this structure here, what we're going to do is try and figure out what the state of the disk, what the log looked like, and then what these data structures would look like in these different phases. Okay, so I'm just going to write out the log records. Hopefully this will be not surprising. We're just going to write them out in the order that we sort of wrote out this transaction history here. Okay, so the first thing that happens, so SOT is the start of transaction. Okay, so log number 1, transaction ID 1 starts. Okay, then transaction ID updates this record A. Okay, notice that we're keeping track of this in this log. In these log records, we've added this thing called previous LSN. Previous LSN is just the previous log sequence number that this transaction wrote. Okay, so we're using this as a way to, if we were to follow previous LSNs in backwards order, we could walk through the kind of walk through all the operations that a given log record wrote. All right, and we have some data, this undo and redo data, which I'm just showing on this example as the page number that we affected, which was A. Okay, so the next thing we do is write this record B. Okay, the next thing we do is we write a checkpoint. So we do explicitly write log records for checkpoints in Aries. So this checkpoint information, again, remember, is just going to be the state of the transaction table, of the dirty page table as of the time that the at this point in time. Okay. Then we're going to write the start of transaction 3. Okay. Then transaction 1 goes ahead and updates C. Okay. Then we do the flush. And notice that so this flush is this dotted line here. Notice that we don't actually write any log records for the flush. So the next thing that is going to appear in this transaction is going to be the start of transaction 2, and then this update of D on behalf of transaction 2. So the flush doesn't appear as a log record, even though it happened to the state of the disk. Okay, and then we just keep going along. So then transaction 1 finishes, transaction 2 updates this value B. Transaction 3 updates B, transaction 2 updates A, and transaction 2 finishes, and then finally transaction 3 writes this value E. Okay? So if you look at the previous LSNs just let us walk backwards through the operations of a given transaction. So for transaction ID 3, I can follow the previous LSN back. So LSN 10 is the previous LSN that transaction ID 3 wrote, and LSN 5 is the first LSN that belongs to transaction ID 3. Cool? Okay, so now let's look at what the data structures on disk would have looked like as this transaction ran. Okay. So the transaction table, remember, is going to record the last LSN, which is the last sequence number that a given transaction wrote. Okay, and we're just going to update it as the transactions run. So transaction ID 1, it's going to be running. It's going to start with log sequence number 1. Then it's going to do when it begins. Then when it writes A, it's LSN. If you just follow along this log here, the next LSN that transaction ID 1 writes is going to be 2, and then it's going to write 3, and so on and so forth. Okay, so we're just going to maintain this kind of table as we chug along. Okay, so eventually transaction ID 3 is going to start. It's going to have the last LSN of 5. Okay, so this thing is just going to chug along until wherever we are at the point that the crash happens. When the crash happens, the only transaction ID that was active was transaction ID 3, and its last sequence number was this sequence number 13. Make sense? You guys understand how this data structure is kind of evolving. Hopefully it's not too complicated. Okay, and then the dirty page table is just recording all the dirty pages and the first transaction that dirtied them. Okay, so transaction ID 1 dirties pages 2 and 3, right? Transaction, and then it dirties as a part of log sequence number 6, it dirties page C. Okay, at this point in time, just after we dirty C, right, transaction ID 2 starts, and then we flush. Okay, so what flush does is it affects the kind of state of the pages on disk. So remember, these pages on disk have this page LSN attached to them. So when we take this flush operation right after transaction ID 2 starts, we're going to take all the things in the dirty page table and write them back onto disk, and we're going to write the page number of the most recent operation that updated that page into disk. Okay, so we're going to update the pages on disk, and then we're going to empty the dirty page table. Does that make sense?
Should flush be in the record itself, like in this stuff?
We don't write flushes into. We're not required to write flushes into the record. It's arguably you could make the recovery process a little bit simpler if we had, but it would make the log bigger. So we'll see how this complicates. It's going to complicate things a little bit. The fact that we don't write log for it. Okay, and then this kind of continues along. So page we then do this write to D. Then transaction 3 does this write to B. Then transaction 2 does this write to A, and then finally transaction 3 does this write to E. Okay. So that's what the state of the system looked like at the time that we crashed, right? We also wrote out this transaction table and this dirty page table when the checkpoint happened, okay? And we're going to record checkpoints in sort of a special place on disk that's going to be pointed to by the log record, and we'll probably, the system needs to do something to explicitly store the location of the last checkpoint. So it needs to have a well-known location, like a specific disk block, where it stores a pointer to the most recent checkpoint that the system took. And in the checkpoint, all we do is write out the transaction table and the dirty page table. Okay, and so we took the checkpoint right here after transaction ID 1 had written A and B. Okay, so the only transaction that was running at the time the checkpoint was this transaction ID 1, okay, and the transaction table, the TID at the last LSN of transaction ID 1 at that point that we took the checkpoint was just 3, right? So we took the checkpoint right after we wrote log record 3. So all we have to do is put this 3-1 there. And the dirty page table similarly only reflected these two dirty pages, A and B, that transaction ID 1 had written at that point. So it doesn't reflect any of the other pages that were dirty after that. Cool? Okay, so now let's see how we actually do recovery. So we're going to go through these 3 phases, as we've already mentioned, analysis, redo, undo, okay? Again, the point of analysis is basically to kind of figure out what needs to be done. So specifically, what we're going to do during analysis is rebuild the try and reconstruct the dirty page table and the checkpoint and the transaction tables so that we can use them for recovery. Right? Then we're going to do the redo pass, this repeating history thing. So again, the thing to realize about repeating history is that what it basically means is that we're going to redo both the transactions that committed and the transactions that aborted. So we're going to be, after we do this repeating history, we should be at exactly the state we were in when the system crashed. Okay? And then what we can do is just undo those logical operations of the losers, the transactions that had not committed as of the time the crash occurred. All right. So let's see what analysis does. So first of all, analysis is going to begin from some start of time forward. So we're going to play the log forward, and we're basically during the analysis phase we're going to update these dirty page table and transaction tables. Okay. So where should I begin my analysis from?
4.
So from the last checkpoint. So I could obviously begin my analysis phase from the very beginning of time. Okay, but the thing to realize is that the checkpoint, I don't actually need to, I'm not going to need to start from the very beginning because the checkpoint is going to, during the analysis phase, trying to figure out what transactions were running and what pages were dirty. And so the checkpoint is like already sort of captured that information for me. So I can start from the checkpoint and start playing forward. Okay, so I start from the checkpoint. And then I'm just going to run these things forward. So what I've just shown here is I've just truncated the log to start at LSN5, and I can just run the checkpoint forward. So I load from disk the state of the checkpoint and the state of the transaction table in the checkpoint, the state of the dirty page table, and I've got whatever I have on disk, right? So remember when recovery starts, so this is sort of the information I have at the beginning of recovery when I load the checkpoint information. Now I just sort of start rolling forward. Okay, so I update these data structures as I go. So transaction ID 3 starts, transaction 1 updates C, transaction 2 starts, transaction 2 updates D, and so on and so forth. I just play this forward and I get this kind of data structure that you see here. I get this at the end of this after playing this forward. So what's a little bit surprising, I said we were going to try and reconstruct the state of the dirty page table. Look at what the dirty page table is here and what we sort of figured out the dirty page table was at the state of the crash. So what's different? I mean, you can see, right, that like A, B, and C are in the dirty page. A and B have different pages here, and C is in the dirty page table, but it wasn't actually in the dirty page table at the state of the crash. So we didn't actually succeed in exactly recovering the state of the dirty page table as of the time of the crash. So why is it different? She said you need to redo the uncommitted operations. Not really. For example, why is C in this dirty page table here, but was it not in the dirty page table at the time that we crashed? Yeah.
Didn't clear the...
It wasn't because of the checkpoint. It was because, why was it? Because of the flush, right? So we took this flush that wrote the state of A, B, and C back to disk, right? So A, B, and C with LSNs 2, 3, and 6 got written back to disk. But we didn't record that information in the checkpoint because we took the checkpoint before the flush operation happened, right? And we didn't, as was asked, we didn't actually write the flush operation into the log. So if we'd written the flush operation in the log, maybe we could have guaranteed that the dirty page table would have been perfectly consistent. But it's not. Instead, the dirty page table is sort of a conservative approximation of what pages might be dirty, right? So if something is in the dirty page table at this point, it's possible it's dirty, and it definitely will include everything that is dirty, but there may be some things that have been flushed to disk that are not reflected in the dirty page table. Does that make sense? Because we didn't go and look at all the pages on disk during recovery. And why didn't we do that? Because we want to just scan this little bit of the log that we're looking at. We don't really want to go have to scan the entire database system and look at the page LSNs of every page in the entire database system, because that would be a very expensive operation. If we had done that, of course, we would have a perfect picture of what the dirty page table looked like. But we'll see how we sort of work around this approximate thing in just a minute. Okay, so now let's talk about how we do redo. So okay, the things that were in the transaction table at the time of the crash, those are the things that we need to, those are the losers, the transactions we need to undo. As I've already noted, the dirty page table doesn't necessarily reflect the true state of pages that are on disk. So these operations 2, 3, and 6 actually have already been flushed to disk, even though the dirty page table doesn't reflect that. Okay, so now let's talk about how we do redo. So redo is going to be about reapplying these operations. And let's see how it works. Okay, so the first question is, where should we start redo from? So is it sufficient, you might say, from the checkpoint? Is it sufficient to start redo from the checkpoint? Yeah.
From the start of the first transaction in the checkpoint's transaction table? Because it was ongoing and you need to replay it?
Well, okay, so that's close, but think about, right, so what we have to replay, right, so think about the operations that we might potentially have to reapply, right, and what tells us, and you kind of have to think about what the semantics of these different fields are here, but like what tells us what operations we might have to reapply? So if you think about like kind of what's in the dirty page table, right, the fact that a page was dirty at the time we crashed, right, suggests that there was a modification that we made to the database that may not have been flushed back to disk, right? Because, so the dirty page table actually perfectly, we're repeating history, right? So the fact that something was in the dirty page table had been dirty means that this was an operation that might have to be reapplied. And I say it might have to be because remember, the dirty page table is not a perfect reflection of what is actually on disk, right? The dirty page table is this sort of approximation of what's on disk because we didn't explicitly record when we took the checkpoints what we wrote to disk. Does that make sense? Okay, so then where should I start recovery from? 2. Okay, good. So we want to start from 2 because it's the smallest recovery LSN. It's the earliest thing that any outstanding transaction had dirtied in the checkpoint, in the log. Okay, so we start from 2. The minimum recovery LSN that appears anywhere in the dirty page table. Okay, so then the question is, okay, what do we actually have to redo? And we need to be a little bit careful. First of all, we'd like to avoid redoing stuff that has already been done, right? Because having to go to disk and like write stuff to disk, having to physically go to the disk and update it, it's going to make recovery slower. So we'd like to avoid repeatedly redoing things. The other thing is that it turns out, at least the paper claims, and it's a little bit hard to wrap your head around exactly what's going on here. I have to, like, it's always confusing, but they claim that that for whatever reason, because of the way that they do this escrow logging thing, that they don't actually want to redo these operations. So somehow, even though they say we're doing physical update logging, right, the physical redo logging, they want to allow these escrow operations, which are like increments or decrements, to sort of still be redone in a logical fashion, right? And so because of that, they need to be careful to not redo these escrow increment or decrement operations. And it's a little bit hard. They have some model of what these escrow operations are, and I can't at least decipher what they really mean by staring at the paper. I've stared at this paper a lot. So the paper is, I encourage you guys to read it as sort of a thought exercise in a paper that is on one hand like a gold standard reference paper, and on the other hand, like at times completely inscrutable. It's like these people who are so absorbed in their little problem, like they've thought about this problem for so many years that they write out all these details and they just like vomit out all these details, and they don't really give you the like high level picture or exactly explain the details. So probably if you followed the 300 citations that they had and read them all, you could really understand what they meant, but it's very hard to follow this paper and to get the lowest level of detail. You can get the gist of it though. All right. Okay, so what do we need to redo? Well, we don't want to redo everything. So what do we actually need to redo? So let's look at the state that we have and figure out what the conditions are in which we have to apply the redo record. So I'm going to read a log record from disk, right? So I'm starting from some log record, like I read this log record 2 from disk. So redo, remember, starts at log record 2. So I read log record 2 from disk. Do I need to reapply this? Do I need to redo this log record? I don't. Why don't I?
LSN is 1.
Okay, well, this LSN2, sorry, this LSN2, right? Okay, so it updated page A. So I don't have to redo that. Why don't I have to redo that? What is it about the state that I have here that tells me I don't have to redo it? Yeah, it's on disk basically. So exactly if I look at the disk, right, I can see if I were to go read this page from disk, I would find that this page this page record A had a page LSN of 2. Okay, so that's the simplest criteria. I can go read the pages from disk. Right, but we'd like to actually avoid going to have to read the page from disk it's going to be a little bit slow. So I'd like to avoid even reading the page from disk sometimes, and there are going to be some conditions where I can do this. Okay, so the first one is that if the page is not in the dirty page table at all, right, then, well, I know that this page can't possibly be dirty, right? So if I'm, I read an update, if I come to some, and there's no examples of this in this trace that I've given you here, but suppose there were some other, log record F, right, that didn't appear in the dirty page table, and I encountered, that log record F while I was doing recovery. Well, or an update to that page F while I was doing recovery. Right, then I would know that I didn't need to I don't need to actually redo any modification to F, because F doesn't appear in the dirty page table, which means that it must have been flushed to disk, right, prior to the latest checkpoint that I took. Does that make sense? Okay. Okay, so there's another condition like this. Can anybody see the other possible condition under which I might not have to reapply something? All right, so the rule is if the LSN of the page, and this is a little bit trickier, but if the LSN of the log record that I'm reapplying is less than the recovery LSN, right? So you might wonder, how that could ever happen. So it could happen, and again, it doesn't happen in this particular trace that I have here. But if a page, I'm reading along, right? And so imagine that I have some log record. I read a log record for, that there's, LSN4 instead of being a checkpoint or something. Imagine LSN4 was a update to page C. Okay. So if the LSN is an update to page C, I would look at page in the dirty page table, and I would see that actually the dirty page table, the entry for C is 6. So I'm looking at LSN4, right? So I know that I don't need to reapply LSN4 because that LSN must have already been reflected on disk, because the recovery LSN is the earliest log sequence number that modified, any page that has yet to be flushed back. So if the recovery LSN for page C is 6, that means the last unwritten modification of C is 6. And anything earlier than that that corresponds to C in the log has already been reflected and flushed on the disk. Okay? So we have these two criteria plus the one that we said, which is the LSN is less than or equal to page LSN. So I can go actually look at the disk, and if the page on disk already reflects the update, then I know I don't need to reapply. Otherwise, I have to reapply. Okay? So I just walk through the log in this way, and I just start redoing records. So I start at log record 2, I check it, and I say, nope, looks like this disk already reflects LSN, page record A already reflects LSN2, don't have to reapply this record. Okay, similarly for B, this update to B, and similarly for this update to C. So these little cancel signs mean we don't have to reapply it. Okay, and then we do this update. So this little sun icon means actually we do have to reapply this update. Okay, so we're going to go ahead and so notice that as we did these, as I checked these log records, I can go ahead and update the dirty page table, right? Because at this point I've actually read those log records, and I've seen that those pages already reflect the state that was in the dirty page table. So I know what the true state of the dirty page table is, right? As we do this. All right, now I do an update I check this update to page D. Right, now I can reapply this update to the database system. At this point, page D when we're running this recovery, we don't actually have to, so I had to reapply this update to page D, to data item D, because the disk page LSN, we don't know what it was, and the dirty page table told us that we were supposed to dirty it. And in fact, we hadn't flushed D back to disk at the time of the crash, so it's a good thing we reapply it. Notice that I didn't remove D from the dirty page table at this point, and the reason for this is that as we're running recovery, it's sort of like we're running in the natural state of the system. We can actually be flushing pages back asynchronously in the background as we do recovery as well. We're not required to force all of our updates to disk during recovery. So D, we've reapplied it, but D is now just a page in memory that is dirty. It hasn't necessarily been forced to go back to disk. Okay? So we're sort of maintaining the dirty page table as we run. We do the same thing for B. When we read B and we put it back in the dirty page table. Similarly for A, and similarly we check E and we have to reapply it. Okay, so now the kind of cool thing is if you look at this dirty page table here after we've done redo, in fact now the dirty page table exactly matches the state of the dirty page table at the time of the crash. So we've exactly got the system back to where we were just prior to the moment of the crash. Okay, and now all's well, and we can do our undo pass. And the undo pass is pretty much straightforward. We just use the previous LSNs to walk backwards through the state of transaction ID 3, which is the one that aborts. Okay. So let's watch how that works. So we find transaction ID 3. We know that its last LSN is 13, so it's starting at log sequence number 13. We walk backwards through the log by following these previous LSN pointers. Okay, and there are only two things that it has only these two updates. Doing an implementation of something that walks backwards through the log in this kind of random access way, of course, it's like you have to think a little bit about how to do an efficient implementation of this. It's likely that what they do is actually carve the log up into sort of, relatively large physical extents, like extents of a megabyte or something each, and they keep the first sequence number and the last sequence number in each one of those extents, and then they can kind of thread backwards by, reading the, they have some way of sort of mapping from a physical log record to which extent it's in, and then they can go read the physical extent and then offset to that log record. So you can sort of imagine how you might implement this in a way that doesn't require you to do a ton of random I/O to thread backwards through the log. And of course, if you're doing this undo, you can undo multiple transactions simultaneously without doing a separate pass for each one. You sort of take the smallest last sequence number of all the transactions that you're undoing, and you undo that. And so you can sort of walk through them in backwards order and undo them together. Okay, so that's the basic protocol. Other questions? All right, so hopefully that wasn't too painful. I think the slides, I used to do this on the board, and boy, it was really tiring. So hopefully, like having the slides that you guys can go reference and walk through will make it a little bit easier to kind of understand what's happening. So there's a couple of little details that we need to talk about. So okay, so there are two. So maybe we'll talk about the kind of more intuitive one first, which is this notion of checkpoints and when we can truncate the log. Okay, so thinking about the dirty page table and the transaction table, like what's the oldest log record? If I show you this, let's go back. If I show you this dirty page table here, right? What's the oldest log record that I absolutely have to keep around? If I know that this is the state of the dirty page table. Well, we sort of have this, we said, I said I didn't mean this to be a trick question. I told you, where do we start recovery from? So where do we start recovery from? Well, we said we started from 2. So we started from 2 because 2 was the earliest thing that appeared in the dirty page table as of that time, right? So basically, we're never going to need to look at any log record that is earlier than either, than the smallest rec LSN in the last checkpoint that we wrote, okay? So if we write a checkpoint out, then we can take anything with a page number, with the LSN that's smaller than the smallest rec LSN in that checkpoint that we wrote out. We can just throw it away, right? So at this point, like we know, for example, that if we were to write a checkpoint right at this point, right prior to crash, then we would never need to consult anything earlier than this, page ID 8 here, right? Because that is the smallest rec LSN that appears in this table. So we can kind of truncate the log prior to this. So all we need to do to truncate the log is periodically flush some pages back and then write these checkpoints. We can flush the pages back whenever we want, in whatever order we want. We can write the checkpoint in a completely, we just have to take a snapshot of the checkpoint and write it back to disk. We don't have to sort of quiesce the system. We don't have to stop the system at all. We just, we're flushing as we naturally go. We write the checkpoints, and the checkpoints will, give us the sort of bound, tell us where we can start recovery from and where we can truncate the log prior to. Yeah?
What if you crash while you're writing the checkpoint? How do you...
Yeah, so there's this, so the checkpoints are small, but you could still crash while you're writing, right? So these systems you can sort of, there's this, like as you start to think about how you actually implement this, you kind of wind yourself into this little recursive loop, but ultimately you have to boil down to the ability to write like a single disk block atomically. So the way that these protocols typically would work is that, remember I said you write the location of the last checkpoint at some well-known place at disk. You don't write the last checkpoint, you don't actually write the contents of the checkpoint, you write the location of the last checkpoint. And fundamentally what we're going to assume is that we can do an atomic disk write of a single sector, which is going to be big enough to hold the location of the last checkpoint in it, right? And so what we'll do is we'll write a checkpoint record, and then we will write the location of, and then we can truncate the log, right? And then we can write the location of the last checkpoint that we wrote. And if we do those things into this well-known location on disk, and if we do it in that order, then we're kind of good to go, because we can, as long as we can do this one atomic disk write, right? If you don't even have the ability to do one atomic disk write, you typically will do things like you will write, you'll have sort of 2 blocks on disk, and you'll write a checksum into each block, and then you can sort of alternate which one you write. So there are 2 locations you check, a primary one and a secondary one, if you check the primary one and the checksum fails, that means you must have like failed while you were updating that block, and then you can go use the secondary one. And the secondary one is guaranteed to be good because you know, somehow you wrote it after you wrote the last primary one or something, right? So you write them both at the same time. So there are these kind of like very fiddly, nitpicky little protocols that people have worked out to make it so you can do this. Okay, other questions? All right, so the other thing, remember, we wrote down these requirements. So I think we've now addressed most of these requirements. Lightweight checkpoints, complex operations, which is why we have to do this physical redo, escrow operations, which we kind of hand-waved at, but you know, one thing we said about escrow operations was that we don't actually reapply all the updates during the redo phase because something about them. And then this crashes during recovery. So the last defect is how we deal with crashes during recovery. And the trick is to write a, as we're recovering, we actually write a special kind of a log record called a compensation log record. The CLR is a compensation log record. Okay. And a compensation log record records the fact that we undid something during recovery. So we write one of these for every operation that we undo, a logical operation that we undo. Okay, and it's a little bit confusing. So these compensation log records, we're gonna, just like we replay all the regular operations, we're also gonna replay these CLR operations. We're gonna redo them. Okay, when we redo a CLR operation, we're actually repeating the undo of some operation that we previously undid. Okay, I'll say that again. When you replay a compensation log record, okay, you're redoing the undo of some operation that you were undoing when the system crashed. All right? So the reason we have to do this is because imagine that you're in the state where you're undoing some operation. Remember, undos themselves are logical. Okay? Now, you get in this weird state where you crashed halfway through undoing something, like, you know, removing an update to an index and an underlying heap file. Right, so now that update to the index is maybe undone, but the update to the heap file hasn't been undone. Okay, so now if you were to go to try to undo that operation, like you crashed and you just started redoing in the way that you had before, you kind of would be in trouble because you sort of mangled this page during the previous undo. You mangled these two things. They're in inconsistent state during the previous undo. Okay, so you actually, the CLR is actually a physical log operation of the undo that you were doing. Okay, it says, for example, I physically modify, to do this undo, I'm going to physically modify this heap file and this index page. And then I'm going to, so that when we're sort of replaying a CLR, we can, you know, make sure that that undo operation that we did is actually physically undone in the contents of the system. I know that this is like, it's confusing because we're sort of mixing up undo and redo in this kind of crazy way. So let me show you an example. So this is just undo that we already saw. Okay, so our loser is transaction ID 3. Okay, so what we do is when we undo this operation 13, we're going to write this CLR record. Okay, so this CLR record, after we undo this operation, or prior to undoing the operation, we write the CLR that has the contents of the sort of modification that we're going to make as a part of the undo operation. Okay, and then it tells us that once we've redone this SLR, redone this CLR operation, if we have to redo it, that we should start recovery, restart recovery by undoing this operation B. Okay, because we've already re-undone this 13 if we happen to need to replay the CLR. Okay, and then similarly, we're going to write a CLR for this B record as we're running. Okay, so we're only going to encounter these CLRs. We only actually have to redo these CLRs, the effects of these CLRs, if we happen to crash in the middle of a recovery, right? But we can sort of replay these CLRs to ensure that the recovery, the effects of the recovery operations are actually, you know, sort of the effects of the undo operations are actually physically, you know, undone in the system itself. Does that kind of make sense? I know it's a little bit tricky, but this will allow us to kind of guarantee that we can properly restart recovery even if we crash mid-recovery. Are there questions about that? What do we write for logical undo? Yeah, is that the question? Like what physically, what do we actually put in a logical undo record? It would typically say something like instead of, so remember the physical record is like, here were the bytes of the page before and here are the bytes after. Okay, the logical operation is like inserted a record X into this database table, right? That's an example of a logical operation. Okay. So a logical undo would be something like remove record with this identifier from this database table. Right? That would be an example of a logical undo operation that would cause us to then go update the indexes and the e-files and everything else as a part of undoing. So obviously the nice thing about these undo operations is that they are, one nice property of them is that they're much less detailed, smaller hopefully than the physical records themselves, because the physical records are likely to be big, and like here are the contents of the pages I've modified. Yep.
Why do we only have 2 CLRs instead of 3? It's going to be 3 steps.
Well, the last CLR, what we would do would be to write some record at the end of this, after we reach, I mean, the last thing is the start of transaction operation. So we probably didn't make any physical changes to the disk as a part of the start of transaction. So that's conceptually why we don't really need a CLR, because we don't have anything to undo in order to undo that start of transaction. You could imagine, and probably most systems do, write some extra log record that's like indicates that a given transaction has been, a given loser transaction, its effects have been permanently undone or something, so that we know that we don't need to re-undo it in some way. But that's a little bit of a detail. Okay? Okay, so that was Aries in like 75 minutes, 60, 70 minutes. So, I want to just, before we finish talking about recovery, I want to just talk about a couple of other kind of recovery issues that things that you might have to deal with. So we've talked about really only one class of failure so far, which is this, the database system was chugging along and then it crashed, right? And then we kind of brought the system back up. We brought it back online. But there's, of course, lots of other failures that could happen in the system, right? There can be random corruptions of memory that could cause the state to be in some really weird state, but the system to continue to run, right? And that would be really bad because, like, the database system might get corrupted, and you'd like to avoid this. And there's lots of techniques that people have developed for dealing with these kinds of so-called Byzantine faults. They typically involve very, very painful things like running simultaneous parallel implementations of the same database system and comparing the results to make sure they're equal so that you can detect when faults like this happen. So like, when the computers in the space shuttle, for example, use techniques like this N-way multi-programming, basically to ensure that like you get really, really, really correct things to deal with these kinds of Byzantine faults. Typically, people don't run database systems in this configuration, although there are these systems, you can actually go buy them today, a system called the Tandem Nonstop SQL system, which is now owned by IBM, was originally developed by Tandem Corporation. It's like 3 simultaneous copies of the memory, the CPU, the database system that all run in parallel, and they compare every operation, do 3-way comparison of every operation and vote. So like every instruction that gets executed, they vote on whether they agree on the result of that instruction. And if they don't, the system halts, because that's better than getting into some weird non-deterministic state. But you can imagine how expensive this hardware is. It's like, hundreds of thousands or millions of dollars for something that's slower than your laptop, because it's custom purpose hardware. Okay, but then there's this whole other class of failures that you might want to survive, like network failures in a distributed case, or more significantly, what you would call kind of disasters, right? So, disaster recovery. Okay, so a disaster is basically, look, if you're running, it may seem silly to you, but if you're running Amazon.com, right, you got to be prepared for the case that like your data center is in the Bay Area and the big earthquake hits, right? Like, and whatever they've been saying it's going to happen for the next 10 years, for the last 30 years, but like it's going to happen someday, and it's going to bring down your data center, right? And it's possibly you're going to lose all the machines that you have there, and if you care about your business, you better be prepared to deal with this, right? So you need to have some strategy for dealing with these kinds of disasters. Of course, giant earthquakes or hurricanes or whatever are less common than just power failures. That power failure a few years ago where the entire eastern seaboard lost power. If your data center happened to be on the eastern seaboard, your company would have been out of business for 2 days, right? So you need some strategy for dealing with this. The typical kind of thing we do is to run what's called a hot standby. And you want to make sure that hot standby is like the half width of a hurricane away from wherever you are, right? So like out of range of the disaster that you want to tolerate. You can imagine, you can come up with risk scenarios. And this hot standby, is basically going to run exactly the operations that your primary database runs. You're going to, maybe ship your database log off to it as you run your operations. It's going to replay them exactly, so that it's in exactly the same state as your database system, so that when the disaster happens, you can do some flip over to that backup. You can start redirecting all your database traffic to that backup, okay? And, making this work really, really perfectly is tricky. Typically, people will accept that, when one of these disasters happens, you might have, some of the outstanding transactions might be lost. You might have a couple minutes of downtime, but okay, all right, there's a couple guys you've got to call up and say, hey, sorry that, hurricane happened. We're not going to ship your package today. Customers are probably going to understand. Like, could you resubmit your order? People get it. What you want to avoid is you're out for 3 days and you can't process any orders at all, right? And so that's the kind of standard thing that happens. So this is basically what we're going to employ is a technique, these replication techniques. And we'll talk much more about replication and how you build a replicated wide area database system in the next few lectures. Okay, so what we've done now, just to kind of recap where we are, we've talked about how to build a single node system that provides these ACID properties. Mostly we focused on atomicity, isolation, and then the last couple of lectures on durability. What we're going to do in the next sequence of 2 to 3 lectures is talk about how we take these ideas from a kind of a single node database system and move them to a distributed database system setting. So first of all, how do we process queries when data is spread across multiple nodes? Second, how do we provide transactions when data is spread across multiple nodes? And then finally, how do we do these things like replication? And then we'll talk a little bit about how this relates to NoSQL and some of the new trends that we have. So in the next couple of lectures, Aaron Elmore, who's a postdoc in my group and going to be a professor at University of Chicago in, I don't know, when you're leaving? June. Is going to give a sequence of lectures on this. He's done a lot of research on it, and I'll be here too. So we'll start that on Wednesday.